Let's talk about destroying something, not a building or a car, something more slippery. Let's talk about destroying information. You write a secret on a piece of paper. A secret nobody else knows. You read it one last time, then you light a match and watch it burn. The paper curls, turns black, and falls apart into a pile of gray ash. The secret is gone. The information is destroyed. Or is it? This question sounds simple, but it's one of the deepest questions you can ask. It pulls together our everyday experience, the rules of computers, and the fundamental laws of the universe. The answer isn't a simple yes or no. The truth is, it depends on who you ask and what you mean by destroyed. In our daily lives, we destroy information all the time, or at least, we think we do. We tear up old bank statements, we delete embarrassing photos from our phones, we forget things we learned in school. From our point of view, that information is gone. It's no longer accessible. It might as well not exist. This is practical destruction. For all intents and purposes, the job is done. But let's go back to that burning piece of paper. You burned it. The words are gone. The paper is gone. But they didn't just vanish. They changed form. The paper and ink were made of atoms. When you burn them, you just rearrange those atoms. They combined with oxygen from the air and became other things. Ash, which is mostly carbon. Smoke, which is tiny particles of soot, and gases like carbon dioxide and water vapor that float away. And heat and light. Every part of that process carries information. The light that shot out from the flame carries information about the chemical bonds breaking. The heat warming the air is just molecules moving faster, and their exact motion is a form of information. The smoke particles, and the ash, and the gases are all the original atoms of the paper and ink, just in a new configuration. Now imagine a supercomputer, a machine so powerful it's beyond anything we can build today. If that computer could track the exact path of every single atom that was part of that burning process, could it reverse the whole thing? Could it follow the smoke, gather the heat, and reassemble the ash back into the paper with the secret written on it? In theory, the answer is yes. The information isn't gone. It's just scrambled. It's been smeared across billions and billions of molecules in the room and in the air outside. It's been converted from a neat, ordered form ink on a page into a chaotic, disordered mess heat and gas. But it's all still there. You didn't destroy the information. You just made it incredibly impossibly hard to read. This is a key idea. Most of what we call destruction is just scrambling. Think about a hard drive on a computer. You drag a file to the trash and empty it. Is the file gone? Not really. Most of the time, your computer just changes a single bit of data in its directory. It's like erasing a name from the table of contents in a book. The chapter is still there, but the computer no longer knows where to find it. It marks that space on the hard drive as available. The ones and zeros that made up your file are still physically there, sitting on the magnetic platter, until the computer decides to write something new over them. This is why data recovery software works. It ignores the table of contents and just scans the whole drive, looking for patterns that look like files. It can often find and reassemble your deleted information perfectly, so you get more serious. You use a special program to whip the drive. This software doesn't just mark the space as free. It actively writes new data over the old data, maybe all zeros, or all ones, or random patterns. It does this over and over. Now is the information gone, it's much, much harder to get back. You've essentially buried it under a mountain of new information. But some physicists would argue that faint magnetic traces of the original state might still exist. With an electron microscope and a lot of patience, a spy agency might be able to recover tiny fragments. The information is still there, just fainter, so you take the most extreme step. You take the hard drive and put it in an industrial shredder. It gets chewed into tiny metal slivers. Then, you melt those slivers in a furnace. Now it's gone, right? The physical arrangement that held the ones and zeros is obliterated. But again, you've just scrambled it. The atoms that made up the magnetic platters are now mixed together in a lump of metal. The information about the files has been converted into the specific, chaotic arrangement of those atoms and the heat that was released when they melted. It's not gone from the universe, it's just useless. This difference between practically gone and fundamentally gone is where things get really interesting. Our intuition is all about practical reality. Physics, however, is concerned with the fundamental rules. And according to physics, information is very, very hard to kill. There's a deep principle in physics that's a lot like the conservation of energy. The law of conservation of energy says you can't create or destroy energy, you can only change its form. Well, many physicists believe the same is true for information. Information, at the most basic level of reality, cannot be created or destroyed. It can only be transformed. This idea comes from how the laws of physics work. The laws that govern how particles move and interact are, at their core, reversible. If you know the exact state of a system right now, the position and momentum of every single particle aspects, you can use the laws of physics to run the clock backward and see what state it was in a second ago or a year ago. You can also run the clock forward and predict what it will be doing a second or a year from now. This is called determinism. If you can always, in principle, reverse the process to find out what came before, it means that no information about the past can ever be truly lost. It has to be encoded somewhere in the present state of the system. The information about the secret on the paper is still encoded in the positions of the ash and smoke particles. The information about your deleted file is still encoded in the faint magnetic remnants on the hard drive. It's a core part of the universe's bookkeeping. Nothing gets thrown away. Then quantum mechanics came along and made things weirder, but also strengthened this idea. In the quantum world, things aren't as certain. A particle doesn't have a definite position until you measure it. Instead, it's described by something called a wave function, which is basically a cloud of probabilities. This wave function contains all the information about the particle, and the core rule of how quantum mechanics works over time, the Schrödinger equation, is perfectly reversible. It's a property called unitarity. It means that as a quantum system changes, the information in the wave function is shuffled and rearranged, but the total amount of information stays exactly the same. It never leaks away. It never vanishes. It gets spread out. It gets entangled with other particles, making it impossible to read in a simple way, but it never disappears from reality. So, for much of the 20th century, physicists had this beautiful, solid principle. Information is conserved. It's a fundamental part of reality. It can be scrambled, but never destroyed. And then they ran into the biggest, baddest information shredder in the universe, a black hole. A black hole is what's left when a massive star collapses under its own gravity. It's a region of spacetime where gravity is so intense that nothing, not even light, can escape. It has a boundary called the event horizon. Anything that crosses the event horizon is lost to the outside universe forever. So what happens if you take our book with the secret written in it and throw it into a black hole? The book crosses the event horizon, and then it's gone. The information that made up the book, the arrangement of atoms in the paper, the chemical structure of the ink, is pulled into the singularity at the center of the black hole, a point of infinite density where our laws of physics break down. From the outside, all you know about the black hole is its mass, its spin, and its electric charge. That's it. It doesn't matter if you threw in a book or a chair or a spaceship. The black hole just gets a little heavier. The specific complex information that made the book a book seems to have been completely erased. This was a huge problem. It created a direct conflict between the two pillars of modern physics. Einstein's theory of general relativity, which describes black holes, seemed to say that information could be destroyed. But quantum mechanics, our best theory of particles and forces, insisted that information could never be destroyed. This clash is called the black hole information paradox. For a long time, people thought maybe the information was just hidden inside the black hole. We can't see it, but it's still there, locked away. But then Stephen Hawking made a groundbreaking discovery. Hawking showed that black holes are not completely black. Due to weird quantum effects near the event horizon, they leak. They emit a faint glow of radiation, now called Hawking radiation. This radiation causes the black hole to slowly lose mass. Over an incredibly long time, trillions and trillions of years, far longer than the current age of the universe, a black hole will completely evaporate and disappear. And here's the killer part of the paradox. Hawking's original calculations showed that this radiation is thermal. It's random. It's a featureless hiss of energy. It contains no information about what fell into the black hole. It's the same regardless of whether the black hole was formed from a star, or from a library full of books, or from a pile of diamonds. So the process looks like this one. You have a book, it contains information. 2, you throw the book into a black hole. The information is inside. 3, the black hole slowly evaporates, releasing only random information-free radiation. It didn't come out in the radiation because the radiation was random. It seemed that the black hole had truly fundamentally destroyed the information. It had violated one of the core principles of quantum mechanics. This was a crisis for physics. It meant that either general relativity or quantum mechanics, our two most successful theories ever, had to be wrong in some fundamental way. For decades, physicists battled over this. Stephen Hawking himself was a firm believer that information was destroyed. He made a famous bet about it with other physicists, but the tide has turned. Most physicists today, including Hawking before he died, came to believe that the information must somehow escape. The big question is, how? This has led to some of the most mind-bending ideas in all of science. One of the leading ideas is called the holographic principle. It was developed by physicists Gerard Hooft and Leonard Susskind. The idea is that the information about what falls into a black hole doesn't actually make it to the center. Instead, it gets smeared out and encoded on the surface of the event horizon like information stored on a two-dimensional computer chip. Think of a hologram. It's a 2D piece of film that can project a 3D image. The holographic principle suggests the universe might be like that. All the information about a 3D volume of space, like the inside of a black hole, can be stored on its 2D boundary, the event horizon. So when you throw the book into the black hole, its information gets imprinted on the event horizon. Then, as the black hole evaporates, the Hawking radiation that comes off isn't perfectly random after all. It contains subtle, incredibly complex correlations. These correlations carry the information from the event horizon slowly back out into the universe. The information isn't destroyed, it's just held for a very long time, and then released in the most scrambled, garbled form imaginable. If you were sitting outside the black hole, you'd never be able to decode it. It would look like random noise. But in principle, the information is all there. The universe's books are balanced. Quantum mechanics is saved. This isn't the only idea. Some have proposed that when a black hole evaporates, it doesn't disappear completely. It leaves behind a tiny, stable remnant that holds all the information. Others have suggested that the information escapes into a baby universe that buds off from our own. Another more violent idea is the firewall. This theory suggests that the event horizon isn't a calm, quiet place, but a raging wall of fire that instantly incinerates anything that tries to cross it, releasing its information back out. There's no final answer yet. The debate is still one of the hottest topics in theoretical physics. But the general consensus has shifted. Most believe that information is not destroyed. The universe, even in the face of a black hole, doesn't throw anything away. It just has a very extreme filing system. So what does this all mean for us back here on Earth, far from any black holes? It means we have to think about information in two different ways. There is the human world of practical information. This is the world of memories, books, hard drives, and languages. In this world, information is fragile. It can absolutely be lost. Think about a human memory. A memory isn't a thing, it's a pattern. It's a specific configuration of connections between neurons in your brain. When a person dies, their brain decays. Those connections break down, the pattern dissolves, the atoms that made up the brain are still part of the universe, but the incredibly complex structure that held the memory of your first day of school is gone. Is that information destroyed in the fundamental physics sense? No. In theory, a superbeing could track every atom as it disperses and reconstruct the brain to see what it once held. But in any meaningful practical sense, the memory is destroyed. The pattern, the useful part of the information, has been lost forever. The same is true for the genetic information of an extinct species. The DNA of the last dodo bird contained a unique sequence, a blueprint for a living creature that had been refined over millions of years. When that last bird died and its body decomposed, that specific sequence was lost to the world. The individual atoms of carbon, hydrogen, and oxygen are still around, but the information, the order they were in, is gone. We could try to piece it back together from fragments, but we can never be sure we got it exactly right. We've lost the original. This is the key difference. Physics cares about the atoms. We care about the patterns. For us, the destruction of a pattern is the destruction of information. But the digital age has added a new twist to this. It has made information both more fragile and more resilient than ever before. On one hand, digital information is just a string of ones and zeros. It has no physical substance. A magnetic pulse or a server crash can wipe out a masterpiece. A single click can delete a lifetime of work. In this sense, it's very fragile. But on the other hand, digital information is almost trivial to copy perfectly. You can make 1 million copies of a photo and store them all over the world in an instant. The original is no different from the copy. This creates a new kind of permanence. Think about that secret written on the paper. In the old world, burning that one piece of paper was enough. Today, that secret might be in an email. That email exists on your computer. It also exists on the server of your email provider. That server is backed up probably to multiple other servers in different locations. It was also temporarily stored on every router it passed through on its way across the internet. Destroying every single copy is a nearly impossible task. In this way, our technology is making it harder to practically destroy information. The internet acts like a great global memory, refusing to forget. Things we wish would disappear in old, embarrassing posts. A false rumor can persist for decades, copied and archived in ways we can't even see. We've created a system that mimics the universe's own reluctance to let things go. So, where do we end up? Can information truly be destroyed? If by information you mean a specific useful pattern, the words in a book, the data in a file, the memory in a mind, then yes, it can be destroyed. We do it every time we burn a letter or forget a name. We destroy the pattern and scatter the underlying components, rendering the information lost to us forever. This is the human scale. But if by information you mean the fundamental quantum level data of the universe itself, the exact state of every particle, then the answer seems to be no. The laws of physics are built on the idea that this information is permanent. It is shuffled, scrambled, hidden, and thrown into black holes. It is converted from simple order to mind-boggling complexity, but it is never, ever erased from the cosmic ledger. The universe remembers everything. The burning paper is a perfect symbol of this split. You watch the flames and see an act of destruction. A physicist, with imaginary supervision, sees an act of transformation. You see an ending. The universe sees a reorganization. You see the information gone. The universe just sees it move to a different file, a file so large and messy that you can never hope to find it again. But it's not deleted, it's just archived permanently.